I'm back, and so are you, because if you weren't back, you wouldn't be hearing me say that. So welcome back. This is part 2 of senses and perception. In the last video, we learned about sensation versus perception. We learned about stimulus, transduction, interpretation. What was the other one? Perception. We learned about how vision works. We learned about how smell and taste works. Today, we're going to focus on hearing. How does hearing work? Before we talk about that, though, let's talk about sound. What is sound? Well, sound is just moving air. Sound is waves of compressed air. So you hear my voice right now, and that's because my vocal cords are wiggling because I'm pushing air over them, air coming up from my lungs, and my wiggling vocal cords are creating waves in the air. In the air, those waves pass through the air to my computer, which records them and digitizes them. And then when you play the video, there's little speakers in your headphones or in your computer that wiggle the same way, in the same way that my vocal cords wiggled, and they recreate those waves of air. So sound is just waves of air. Your ear is responsible for collecting those waves of compressed air and converting them into a nervous signal to send to the brain, and then your brain perceives the sounds. So that could be music, it could be my voice, and it perceives the meaning, or it basically labels what those sounds are. Or that's the sound of someone hammering, or that's the sound of a chainsaw. Okay, let's talk about sound in a little bit more detail. So the waves of compressed air that make up sound, they can vary in their amplitude. So you can see here, amplitude is basically how high or how powerful these waves are, how big they are. And we measure amplitude in decibels. So if something is soft and you can barely hear it, then the amplitude is going to be small. And if you talk really loud, or you go to a Rolling Stones concert or something, after the coronavirus thing is over, of course, then you're going to hear loud sounds, and that's because the amplitude is much higher, right? Higher decibels. The frequency of the sound, so the number of waves per unit of time, corresponds to how we interpret pitch. So if you hear a note that has a long wavelength of sound waves, then it's going to register as a low note or low pitch. And if it has a higher frequency, then it's going to register as a higher pitch. So amplitude and frequency affect the types of sounds that we hear. So how does hearing work? I made this. This is pretty cool. So here you are. Here are your ears. Here's your brain. These are sound waves. Here they come. So they hit your ears. Your ears collect the sound waves. They vibrate your ears in a way we'll talk about later. They send a signal to your brain, and your brain perceives the music. Right? So the music isn't real. The music is just sound waves that your brain is perceiving. So the music is really just in your brain, and outside of your brain, it's just waves of compressed air. Would an astronaut hear sounds in space? Well, if you take all the air out of the system, so if you're in a complete vacuum, then you're actually not going to hear sound waves, because if there's no air, then by definition, there's no sound. It's a little more complicated than that, but that's the gist. All right, so when our brain receives these signals from our ears, then there's different parts of the brain that are involved with interpreting and perceiving those signals. So basically, again, your brain creates the sounds that you hear. This is an ear. You might just think that this is your ear, but really your ear goes deep into your head, and it's pretty complicated. So the ear consists of 3 parts. Let me go to the next slide. Your ear has 3 parts or sections. This is your outer ear, right? The part that sticks outside of your head. So it's made out of cartilage. It doesn't move. It's kind of boring. And really all it does is collect sound. And what's interesting is if this outer ear is larger, like it is on this cute little guy, look at his outer ear. He's got huge ears, right? Kind of like a baby Yoda going on here, except it's a fox. And so this huge outer ear is going to collect more sounds. So the bigger the outer ear, And typically, the more what do you call it? The better you're going to be able to hear low sounds. If you want to improve your hearing, you can actually do that by increasing the size of your outer ear. So take your hands and put them into like a cup shape, like make the letter C with both of your hands, and then hold them up behind your ear. So basically, they're making your outer ear larger. And now listen to my voice. And my guess is it sounds bigger. It sounds louder. And by the way, if you're wearing headphones, then that whole experiment was a disaster and probably didn't work. The middle ear gathers the sound that the outer ear collected and amplifies it and transmits it to the third part, the inner ear. So the middle ear is kind of the mediator. And so the middle ear has little bones in it that we'll talk about in just a minute, and it also has your eardrum. So your eardrum is this membrane, and so the sound waves are going to get collected, and they're going to come in here, and the sound waves are going to hit your eardrum, and your eardrum's going to wiggle. And as your eardrum wiggles, it's connected to some bones in your middle ear, and those bones are going to wiggle. And all that wiggling is going to influence your inner ear. So your inner ear is going to get kind of wiggled and pushed and punched by the bones of your middle ear, and it's going to take those that energy and basically turn it into electrical signals that get passed along the auditory nerve to your brain. Here it is in more detail. So again, the outer ear is going to collect the sound waves. The sound waves are going to move in. They're going to hit the eardrum, which is a membrane. The eardrum is going to wiggle. The wiggling is going to move the three bones of the middle ear. They're called the malleus, the incus, and the stapes. And so they're going to wiggle. And the wiggling of the stapes is attached to the inner ear. The wiggling of the stapes is going to push on the inner ear. Your inner ear is really interesting. As you see your inner ear here, it kind of coils on itself. This is called the cochlea. And it's full of fluid, and it's lined with hairs. So the pushing of the stapes is going to create waves of fluid. And these waves of fluid are going to go through your cochlea. And as those waves pass over the cochlea, there's little hair cells that are going to get wiggled. And those hair cells are attached to nerves. And the wiggling pattern of those hair cells is going to generate different patterns of nervous signals. And those signals are going to go to the brain, and you're going to hear sounds. Okay, so the inner ear, which you just saw a slice through, the inner ear consists of two parts. So there's the part I already mentioned. There's the cochlea. So this fluid and hair-filled tube that's coiled on itself, it's responsible for hearing. But your inner ear also has these tubes. So there's the tube going, that's horizontal. There's a tube that's kind of vertical, and there's another tube that's kind of at an angle. These make up the vestibular apparatus. Right? So while the cochlea of your inner ear is involved in hearing, this part, the vestibular apparatus, is involved with detecting motion and movement. Right? So it's basically sending a signal to your brain saying, all right, Billy Bob is running, or Billy Bob is jumping, or Billy Bob is spinning, or Billy Bob is falling, whatever. It's how your brain perceives the motion of your body. So we'll talk about both the cochlea and the vestibular apparatus in more detail as we progress. Let's start by talking about the cochlea. So I mentioned the cochlea is full of fluid, right? And it's lined with hair cells. So this is another image of it. Here's another image. So in here there's going to be fluid, and there's these little hair cells. So again, the sound waves are going to wiggle the middle ear bones. The middle ear bone is going to push against this fluid, and then the fluid is going to have waves. Imagine instead of like a tube of fluid, imagine this was a long water-filled balloon. So just like how the stapes is getting bumped by the sound waves and it's pushing against the fluid-filled cochlea, imagine if you were punching this fluid-filled water balloon. It's going to send shock waves throughout the water balloon, and it's going to wiggle. So basically the sound wave gets transduced to waves of fluid in the cochlea. The waves of fluid are going to move through the cochlea, and they're going to move this membrane called the organ of Corti or Corti. And on this organ are little hair cells. and the hair cells are going to wiggle. The wiggling is caused by the movement of the fluid, and the wiggling of the hair cells causes them to send signals, nervous signals, to the brain. If you want to see all this, by the way, you can click on the link on the PowerPoint and watch a good YouTube video of this that probably explains it way better than I am. So it's really the wiggling of the hair cells that send signals to the brain that allow you to hear. And here's a picture of the hair cells inside the cochlea, right? So again, as fluid washes over these, they're gonna wave back and forth, kind of like, you know, stems of grass underwater with waves of water from the ocean washing over them. It's the same concept. If you hear a really loud sound with high decibels and therefore high amplitude of the sound wave, it's going to cause some pretty crazy waves of fluid in the cochlea, and that's going to really wiggle the heck out of these hair cells. So if you listen to music too loud on your headphones, it's going to really wiggle these hair cells, and it's going to it can destroy them or damage them. And so that's one source of hearing loss. In this sad picture, here's normal hair cells in a guinea pig, right? So the waves of fluid are going to wash over them and cause them to wiggle, and they're going to send signals to the brain. They're going to hear, you know, guinea pig type sounds. In this experiment, the researchers blasted, I think it was heavy metal, really loud. These poor guinea pigs just got inundated with Metallica at really high volume. And the intensity of the sounds wiggled these hair cells so much that some of them got ripped up and damaged. And so this guinea pig is going to have some hearing damage. And so I don't know if they installed, you know, hearing aids for this guinea pig. Actually, no, they didn't, because they had to kill the guinea pig to even get this picture of its hair cells. So, and they had to kill this one too to get the pictures of these healthy hair cells. Anyway, I digress. I mentioned the vestibular apparatus is a part of the inner ear that's not involved in hearing. It's involved in detecting motion, but it works along the same principles as the cochlea. So in the cochlea, it's sound waves that create the waves of fluid in the cochlea that lead to hearing. The vestibular apparatus has hair cells, and it's filled with fluid as well. But here, the motion of the fluid isn't caused by sound, it's caused by motion. So imagine, if you will, that you get on a, oh man, I want to say a carousel. What do you call it? You know, the spinny thing and you're at the playground when you were a kid? The tilt-a-wheel, is that what you call it? The spinny wheel. I don't know, I avoided those things because they make me vomit. But if you get on one of those things and you spin, right, the centrifugal force is going to force the fluid in the vestibular apparatus to get pushed out to the sides. So you're going to get a signal from your vestibular apparatus to the brain, and it's going to say, hey, I'm spinning, right? And you're also going to, if you have your eyes open, you're also going to see the world is spinning. So you're going to get data from your vestibular apparatus in your eyes that the world is spinning. Okay, and then what happens when you step off the spinny thing is the fluid is still sloshing around. So you're going to get dizzy. So there, your eyes are going to say, I'm not spinning anymore, I'm walking. But inside your inner ear, the fluid is still sloshing around, and it's sending signals to your brain saying, we're still moving. And so the dizziness that you feel is just that disjunction of signals from your eyes and your ears, and you're going to feel like the world is spinning even though really it's not. Anyway, I hope that was helpful. Another example would be like, let's say you're running, right? If you're running, then this stuff, the fluid in the vestibular apparatus might be sloshing up and down, or might, if you're running real fast, it might get pushed towards the back of your head. And anyway, that's going to send a signal to your brain and say, hey, we're in motion. And your brain's like, cool, I get it, we're running. So vertigo and motion sickness are two things that can happen when the signals from your vestibular apparatus and your eyes aren't in agreement. So vertigo is any sensation of motion in your brain, even though you're not moving. So what's going on here is maybe you've experienced vertigo. Maybe you were up, you were in New York City, and you went to an observation deck high on a tall skyscraper, and you looked down. And when you looked down, you kind of felt like you were falling. You're like you were floating. You just felt this weird sensation. So what's going on there is you're just standing on the edge and you're not moving. So your vestibular apparatus is saying, hey, the motion, the fluid in the vestibular apparatus isn't sloshing around, so I'm stationary. However, your eyes are looking down at that big drop down to the sidewalk below, and your eyes are like, oh man, everything's moving, I'm way up in the air, and it sends a signal to your brain. Your brain is like, I'm not sure, should I trust my eyes or should I trust the vestibular apparatus? And so your brain kind of freaks out and you get the sensation of vertigo. Motion sickness is similar, it's just the opposite of that. And I've already described this really. Here's that tilt-a-wheel thing I was talking. Carousel? Carouwheel? What the heck, man? What is that thing? I'm going to think of it as soon as I post this video. Where was I? So if you get on this thing, once again, or if you're in a car, let's go with a car example just to mix it up. Let's say you're in a car and you're going 65 miles an hour down the highway. Your vestibular apparatus is going to get, or maybe you're on a curvy road. As you go around the curves in the mountains, your vestibular apparatus is going to get moved and the fluid in it's going to get sloshed around. So it's going to send a signal to your brain and say, hey, we're moving. But your eyes, maybe you're reading a book on the inside of the car, your eyes are going to say, you know what, I'm reading this book and you know what, I'm not moving. So your brain is like, oh man, what's going on? Am I moving? Should I listen to the vestibular apparatus or am I not moving? Should I listen to the eyeballs? And so your brain freaks out and you start getting motion sickness. How do you fix or prevent motion sickness? Well, you look out the window. Because when you look out the window, now your vestibular apparatus is saying, hey, we're moving, and your eyes see the moving stuff outside the windshield, and your eyes tell your brain, hey, we're moving, and your brain's like, cool, all is right in the world, and you don't feel motion sick. All right, how do we know where sound is coming from? I made this. So here you are, right? And someone over to your right is talking. So when they talk, the sound waves are going to leave their mouth and they're going to spread throughout the room and they're going to bounce off the walls and whatnot. So watch this. Ooh. So what happened is, let's do it again. So when the sound waves leave their mouth, you'll see that they bounce off and they hit your right ear a split second before they hit your left ear. So what's really interesting here is if someone's talking over to your right, you actually hear their voice like it should be an echo because your right ear is going to hear what they're saying a fraction of a second before your left ear hears what you're saying. Right? And what's interesting is your brain picks up on this, or your brain filters the information in a way that it fuses those two sounds into one. So if you hear a sound that's coming from the right side, then your brain is going to actually hear two sounds, but it's going to fuse it into one, and you're only going to perceive one sound. And instead, what your brain does is it says, hey, I just hear one sound, but you know what? It's coming from the right. Does that make sense? So if you close your eyes and someone was to, sneak up and clap on your left side, your left ear is going to hear the clap before your right ear, but you're just going to hear one clap. You're not going to hear an echo, and your brain is going to interpret that sound as coming from the left side. It's pretty cool. I talked about how babies probably see the world upside down because it takes their brain a while to flip the world right side up. Well, similarly, we don't know, but we think that infants, when babies are first born, they probably hear everything in echo. So in other words, that infant brain has to learn, okay, you know what, I'm not hearing mama's voice 2 times. I'm just hearing her one voice, the one sound that she's producing, but she's just over on my right side. So it takes a while for the brain to learn to take those 2 sounds that are arriving at a fraction of a second difference in the ears and to fuse them together into one sound that has a directional component. Pretty cool. Okay, so in the first video I talked about sensation versus perception. So let's return to that because it leads to some pretty cool philosophical concepts. So sensation is basically just what comes into your body through your sensory organs. So if you were to look at a cat or listen to a cat or feel a cat, you would get all sorts of different data points. You might see that it has whiskers. You might hear it meowing or hear it purring. And as you touch it, you might feel that it's soft and furry, right? So those are the sensations. And your perception is it's a cat. So in other words, your brain takes the whiskers and the meowing and the purring, and it creates the image of a cat in your mind, right? And so what's cool about this is we can trick how our brain perceives the world. So, so like if let's say it's dark and you hear purring and you reach out and touch and you feel something soft, maybe your brain is like, oh, it's a cat. And then you flip the lights on and really it's your little brother who's purring and he's got like a furry Chewbacca costume on, right? You're going to be like, whoa, and you're going to be surprised. So in that case, your perception of a cat didn't match the reality of your little brother. So your brain is always perceiving the world based on the sensations that are coming into it, but your brain can be tricked. So for example, one way that your brain can be tricked or your perception can be influenced is through drugs. So I already mentioned that you can take some ibuprofen when you've got a boo-boo, and your brain kind of turns the dial down on pain perception. Well, if you drink some alcohol, or you smoke marijuana, or you take some speed or cocaine or heroin or whatever, you're ingesting chemicals that are going to interact with your brain, and those chemicals are going to cause perception of things that aren't there. So someone who uses drugs might hallucinate, or they might hear sounds that aren't there, or they might not hear sounds that are there, or they might see colors that don't exist. So colors that are in their brain but aren't being triggered by the absorption of light waves. So in other words, drugs can affect how we perceive the world. All right, so let's look at some examples. This is going to blow your mind. You've probably seen a bunch of these before. You guys are, internet savvy type people. And let's just look at some mind-blowing examples of how the mind can be tricked. Okay, so the thing to remember as we move forward is, again, you're just not seeing the world as it is. You're seeing the world as your brain is creating the world. So your brain is creating an edited version of the world around you. So your brain might be ignoring the hat on your head or the glasses on your face. Maybe you can hear cars driving down the road, but you didn't really hear them until I mentioned it. Your brain is editing the data that's coming into it, and it's creating a perception of the world that you're experiencing, but it's an edited perception, right? And so again, your brain can be tricked and your perception can be influenced in some really interesting ways. So let's look at this. So if you read this paragraph, right, it's really easy to read. According to a research study at Cambridge University, it doesn't matter in what order the letters in a word are. The only important thing is that the first and last letter be in the right place. So even when you're reading, you're not actually reading the word letter by letter. Your brain is kind of taking the overall impression of the word and linking it up with a word that you already know. All right, so that's kind of interesting. Oh man, hold up. Can you hear my dog whining? I'll be right back. Okay, I'm back. Just Roger the dog, whining for no reason. He's perfectly fine. I asked him if he wanted to go outside. He just stared at me like an idiot. So he's fine. Thanks for that, Raj. Okay, where were we? So here's another example. How many triangles do you see? 2? Different number? In reality, there's no triangles. There is not one triangle on this picture. All right, so in other words, your brain creates a triangle here, even though one doesn't exist. Your brain creates a triangle here, even though it doesn't exist. So this triangle consists of nothing, but your brain kind of fills it in and creates a triangle. Okay, maybe that's not the best one to start with. Let's look at this one. Is the vertical line longer than the horizontal line? It sure looks like it, doesn't it? It's not. So here we've got some rulers. So you can see the vertical line is 10 whatever millimeters. I don't know what this was. Oh, centimeters. Yeah, 10 centimeters. And the horizontal one is 10 centimeters. So they're the same length. So your brain is basically tricking you. Your perception is that this one is longer, but in reality it's not. Right? And this happens in other examples. This is a pretty famous one you've probably seen before. Um, the two yellow lines are the same width. There it is. Right? But this one looks longer. And it looks longer because there's an illusion. These lines that are simulating like a railroad track give the impression that this is further away. And since it's further away, then since it looks like it's the same size, then it must be bigger. I didn't explain that very well, but I think you understand what I'm trying to say. So, man, that was hard to describe. Let's move on. Same thing. What's longer, this black line or this black line? This one looks longer, doesn't it? But they're not. They're the same length. So again, your brain tricks you. What's longer, this black line or this black line? This one looks longer, doesn't it? But it's not. It's the same length. These guys are the same length. So again, it's an illusion. We're tricking the brain. Perception is not reality. Okay, here we got orange and blue circles. Which one's bigger, this orange circle or this orange circle? This one looks bigger, doesn't it? Ooh, check out this animation I did. Oh, see it again. Oh, so this orange circle and this orange circle are the exact same size, y'all. It's an illusion. Your brain's being tricked. So the presence of these larger circles makes this one look smaller, and the presence of these smaller ones makes this one look larger. So again, our brain is editing our perceptions of the world. If you look at this, these gray lines that are going left and right, they look like they're kind of curvy or wavy or angled, but they're not. They're parallel. So if you put this thing on here, you can see that all of these squares are lined up and the gray lines are parallel. Right? So again, again. It starts messing with your mind, doesn't it? Yeah? Whew, trippy. Okay, what's going on here? Do you see a blue circle? You do? Okay, well what's interesting is the only blue on this image is here and here and here. So if you kind of see blue everywhere else and it looks like a blue circle, it's not real. So your brain again is kind of filling it in, editing the world that we are experiencing. Is square A darker than square B? It sure looks like it, but it's not. They're actually the same color. So the pixels in square A and square B that are being produced by your computer screen are exactly the same, but your eye is like, oh, or your brain is like, oh, this one's in shadow, so that's making it darker than it really is, and basically it edits the interpretation of these light waves and causes this one to look lighter even though it's the exact same color. What do you see? You see two faces, right? You see a dude looking to the right and a dude looking to the left. And there's no faces there. We just fill it in, right? You see a vase? Do you see both? Do you see a vase and two faces? Okay, whatever. Ooh, this is a famous one. Is it a young lady looking off to the left? So we're looking at her left ear? Or is this a witch or some creepy old lady and this is her eye and this is her nose? Which one is it? So your brain probably kind of flashes back and forth. You're either seeing an old lady or a young lady, and it's difficult. You can do it after a few seconds, but it's difficult to see both of them at the same time. And that's because your brain is being tricked into, well, what is this? What am I perceiving? An old woman or a young lady looking away? Do I need to explain this one? Just look at this. Do you see the flashing black dots, y'all? I do. Well, they don't exist. All of these dots are white. Your brain is just filling in black dots. Ooh, and then finally, so here's the face of a Cheshire Worcestershire cat from Alice in Wonderland, right? So what you got to do is just stare at this X and kind of let your eyes relax. Okay, let's do it. And then you just got to stare for like 30 seconds. Ready? I'm going to do it. I'm staring. Oh. Okay, so for me, as I stare at the X, everything in the background starts to fade except the teeth on this cat's grin. And then if I keep staring, then eventually the teeth disappear and I'm just looking at a black X on a white background. And what's interesting is it goes back and forth. So as your eyes kind of go out of focus, it all disappears and it's white, and then something happens and boom, you can see it again. So nothing's actually disappearing. Just again, the way that your brain is perceiving the world, it's editing your experience, and it's actually causing your perception of the cat to change, making it disappear even though it's not actually doing it. All right, so right now you're looking at colors that don't exist. You're hearing my voice, which is just compressed air. I'm not actually speaking out of your speakers. You're sensing, the chair under your legs or the socks on your feet, even though all that's going on is nerves are getting squished by the clothes you're wearing. All right, that was kind of a lame wrap up, but I hope you get the point. Pretty interesting. All right, cool. Later.